Use this video to kick off our new unit, Chapter 6, and essentially Section 6.1, and the concept of the unit circle, a new way to explore trigonometric functions. And we're going to start by returning to our good old bow tie diagram. We'll recap it very, very quickly. We have a circle of radius r, and you can see our four little symmetry partners, all with related terminal points, x, y in quadrant 1. Negative xy in quadrant 2, negative x, negative y in quadrant 3, x, negative y in quadrant 4. We see four different arcs, red, black, green, blue, all building one of the four bow tie right triangles. Now, other key pieces that we've talked about, well, when we start looking at these and work with the Pythagorean theorem, we came up with some very nice pieces that come out of the bow tie diagram, namely x squared plus y squared equals r squared. That will be true for any point on this circle. And then using some of our SOHCAHTOA language, we also had a very nice way in which we could reflect the value of the sine, the cosine, and the tangent function. The sine is y divided by r, the cosine is x divided by r, and the tangent is y divided by x. So go back and look at your diagram, be familiar with it, and then we're going to add a nice little twist that's going to start to make some of these pieces really come to life in a new way. And how are we going to do that? Well, with the concept of the unit circle. And so what you see here is a stripped down version of the bow tie diagram, a little bit cleaner, didn't draw all the angles, all the different color codings, but you still have our nice set of four triangles. What's different in this diagram is nothing more than the fact that we have now made r equal to 1, hence a unit circle. It's a unit circle centered right at the origin with a radius of 1. So what's the beauty of this? Well, x squared plus y squared equals r squared now becomes, when r equals 1, x squared plus y squared equals 1 squared, x squared plus y squared equals 1. The equation of a circle centered at the origin with a radius of 1 is nothing more than what you see right there. X squared plus y squared equals 1 squared, x squared plus y squared equals 1. And we'll find out that has very nice implications for our sine and cosine function, which in the past we expressed as y over r and x over r respectively. Well, what's the nice thing? When you divide by r and r is equal to our good friend 1, the sine of theta on the unit circle is nothing more than the y coordinate. The cosine of the angle theta is nothing more than the x coordinate. Positive or negative again, depending on what quadrant, what angle we're working at. But this is the beauty of the unit circle. It so simplifies things for us. Again, the key piece, and this will get us into what we'll start doing with our notes as we work through the rest of this package. The unit circle, again, is the bow tie diagram with r equals 1, the equation of the unit circle, x squared plus y squared equals 1. And one other point of beauty, if xy is on the unit circle, satisfies this equation, then so too are the points negative xy, negative x negative y, x negative y. And again, no great surprise. Look at the bow tie diagram, look at your symmetry, and you can see how these pieces work all together. Work our way through a couple quick problems. Find all points on the unit circle given that x equals 1/2. Well, what do I know must be true? I know x squared plus y squared has to equal 1. I know that x is equal to 1/2. So I know that 1/2 squared plus y squared equals 1. This becomes 1/4 plus y squared equals 1. Subtract 1/4 from each side, and I have y squared equals 1 minus 1/4 equals 3/4. Y squared equals 3/4. Let's just write it one more time. Tells me that y equals plus or minus the square root of 3/4. Plus or minus square root of 3/4. Well, I can write this, remember. You can write square root of a fraction as what? Square root of the numerator divided by square root of the denominator. Y equals plus or minus the square root of 3 over the square root of 4, which happens to be 2. y is equal to plus or minus the square root of 3 over 2. What are the points on the unit circle with x equal 1/2? 1/2 positive square root of 3 over 2. 1/2 negative square root of 3 over 2. By the way, you might be seeing some 30, 60, 90 triangle type numbers structured right here with that 1/2 square root of 3 over 2. Find y such the point negative 0.8. Y is a point on the unit circle, by the way, in quadrant 3. Oh, okay. Well, quadrant 3 requires what? Well, let's look over here. Quadrant 3 would be located down here. That's going to require my y coordinate to be negative. My x coordinate I can already see is, they're telling me I got to be in quadrant 3, my x coordinate better be negative as well. Again, x squared plus y squared equals 1 is going to be true. Negative 0.8 squared plus y squared equals 1. 0.64, negative 0.8 times negative 0.8 is 0.64 positive, plus y squared equals 1. Subtract 0.64 on each side. Y squared equals 0.36. Y equals plus or minus the square root of 0.36. And if you go to the calculator, you're going to come back with y equals plus or minus 0.6. I need to have my point be specifically in what quadrant? Quadrant 3. What do I know? In quadrant 3, my y coordinate better be negative. I'm going to want my y to be equal to negative 0.6. That's the value that I need. What's the point on the unit circle such as that satisfies this? My point would be negative 0.8, negative 0.6. Find all points on the unit circle given y equals the square root of 2 over 2. Okay, algebraically, let's solve that. X squared plus y squared equals 1. X squared plus the square root of 2 over 2 squared equals 1. X squared plus square root of 2 times square root of 2 is 2. 2 times 2, 4. 2 fourths plus 1/2 equals 1. Subtract 1/2 from each side. X squared equals 1/2. X equals plus or minus the square root of 1/2. Equals plus or minus, oops, sorry about that. Plus or minus, well, square root of 1 is 1. Divided by what? Square root of 2. You can take square roots of numerator, square roots of denominator. Rationalize to get to your final point, and I'm going to say x is equal to plus or minus the square root of 2 over 2, multiplying top and bottom by square root of 2 over 2. What are my desired points? Square root of 2 over 2, that's my positive x value, and we said y by default was square root of 2 over 2. There's my first point, sorry about that. My second point, let x be negative square root of 2 over 2. And again, y square root of 2 over 2. Those are my 2 points. Find x such that x and negative 0.6 is a point on the unit circle in quadrant 4. Quadrant 4, over here, it's telling my x is going to have to be a positive value. I know that y is. What do I know? X squared plus negative 0.6 squared equals 1. Negative 0.6, negative 0.6, 0.36. X squared plus 0.36 equals 1. Subtract 0.36 each side. X squared equals 0.64. If we remember a little bit work up here in an earlier problem, I know that x equals plus or minus the square root of 0.64. X equals plus or minus 0.8. Where do I want to be? I want to be in quadrant 4. So, what do I know in quadrant 4? X better be positive. So I'll just write need x positive for quadrant 4. What's my point? 0.8, negative 0.6. And we're good. So those are the basics, identifying points on the unit circle. Now, if we come back to our little bow tie diagram, we can feel very comfortable with the following statement that you see here, verifying points on the unit circle. Let's go ahead and do this. A couple other pieces out of the way there for a second. Sorry about that. If xy is a point on the unit circle located in quadrant 1, x and y has to be positive. What else do I know? I know it's three partners, it's symmetry partners, negative x comma y, negative x, negative y, x, negative y. They're all on the unit circle and respectively in quadrants 2, 3, and 4. So, is the point negative square root of 3 over 2, 1/2 on the unit circle? And if so, use symmetry to find its symmetry partners, the other 3 points on the unit circle that would also work. Well, how do I know if this point's good? It needs to satisfy x squared plus y squared equals 1. Let's check this point out. Negative root 3 over 2 squared plus 1/2 squared equals 1. That's what I'm checking. Negative root 3 times negative root 3 becomes 3. 2 squared is 4. 3/4. 1/2 times 1/2. 1/4. Does 3/4 plus 1/4 equal 1? Absolutely. Is this point on the unit circle? It sure is. And so who else can be on the unit circle? Well, that, by the way, looks like a quadrant 2 answer. In quadrant 1, so I'll even mark, there's quadrant 2. Quadrant 1, I'd have square root of 3 over 2, 1/2. In quadrant 3, both my x and y coordinate would be negative. Negative root 3 over 2, negative 1/2. And in quadrant 4, that's my other remaining point I need to get. What do I know? X coordinate's positive. Root 3 over 2 and y coordinate negative. Root 3 over 2 and negative 1/2. And there are my 3 symmetry partners to go along with negative root 3 over 2 and 1/2. Is the point 3/5, 4/5 on the unit circle? Think Pythagorean theorem in the lovely 3, 4, 5 triangle. I bet you're going to think the answer is yes. By the way, that would be quadrant 1 if it is. 3/5 squared plus 4/5 squared equals 9/25 plus 16/25. Last time I looked, 9 plus 16, 25 over 25. It's 1. Yes, it's on the unit circle. There's quadrant 1. Let's find my other points. In Q2, Q3, Q4. In quadrant 2, my x coordinate's negative. Negative 3/5. My y coordinate is positive. Quadrant 3, both values are negative. Negative 3/5. Negative 4/5. Quadrant 4, x is positive. 3/5. Y is negative. Negative 4/5. There's my symmetry partners. One more. Is the point square root of 7 over 4, comma, negative 3/4 on the unit circle? This is Q4, by the way. Let's test it out. Square root of 7 over 4 squared plus negative 3/4 squared. Square root of 7 times square root of 7, 7. 4 times 4, 16. 7/16. Negative 3/4 times negative 3/4 is positive 9/16. 7 plus 9, 16 over 16 equals 1. Yes, it's on the unit circle in quadrant 4. Quadrant 1, both values would be positive. Square root of 7 over 4, 3/4. Quadrant 2, x coordinate's negative. Negative square root of 7 over 4, positive 3/4. Quadrant 3, both values negative. Negative square root of 7 over 4, negative 3/4. And I'm done. So I hope that's given you a good starting point here, understanding what the unit circle is, understanding how you verify that something is on it. X squared plus y squared equals 1 must be satisfied. If so, you've identified a point on the unit circle, you can find its symmetry partners in the other 3 quadrants. Remember, xy, negative xy, negative x, negative y, negative x, y, and then also our last piece, x and negative y. So let me repeat that, I apologize, and we'll go ahead right back up here. xy, first point, quadrant 1. Negative xy will be located in quadrant 2. Negative x, negative y, located in quadrant 3. X, negative y, located in quadrant 4. All right, so a little bit more legwork to do on this unit. First part. It's to remember the concept of arc length. And we're going to find an arc length on a unit circle is going to take us to a point on the unit circle. So a couple things to remember. Remember the formula for arc length. We said arc length S equals R theta. R is the radius of your circle. Theta is your angle measured in radians. There's my sector, or my arc length. If the radius of a unit circle is 1, we get a very simplified result. My arc length is equal to the measure of the angle that is cut, measured in radians. And one thing just to note, going forward, we're going to use the letter T rather than S to represent arc length. So, here's an example of a terminal point, xy. Its arc length would be T radians. Notice that we're going in what direction? We are going in a counterclockwise direction. That always means a positive angle. Here's a terminal point where we have traveled in a clockwise manner. This would be a negative radians angle. We knew that before. Now, in the context of the unit circle, what did we say? We said our value of t, our arc length, is nothing more than the measure of the angle in radians. So, something interesting. Take a look at this first one. Look at that arc. Well, we would call that a pi over 2 radian angle, by the way. And by the way, look where pi over 2 terminates. It terminates at the point 0, 1 on the unit circle. An angle of pi radians, well, goes halfway around the unit circle. Where does it terminate at? -1, 0. An angle that's 3 pi over 2 radians terminates at the point 0, -1. And an angle that is 2 pi in radians, gee whiz, what's it do? It gets right back to where it started from at its initial side, returns to 1, 0. Find the terminal point, some extra problems. Determined by each real number t. If t is equal to 3 pi radians, what would I do? I'd go around my unit circle one full time, and then what do I need to do? Well, half a revolution. So if I go to here, and I'm going to just coil this out a little bit so you can see it, kind of travel. That's a 3 pi radian trip. Where did I wind up at? My terminal point is -1, 0. An angle that is negative pi radians. Let me go to a different color to draw this real quick. I'll go red. I need to go clockwise half a revolution along the unit circle. Where do I wind up? I wind up right at this nice little point. I wind up at -1, 0 again. What we're going to find, these terminal points are actually going to translate into trigonometric values for us very soon. We'll see that when we get into the meat of the next unit note section, part 2, as we build the unit circle. Last one, t equals negative pi over 2. Where do I go? Well, I got to go clockwise. Instead of going pi over 2 counterclockwise, I'm going to go pi over 2 in a clockwise manner. Where do I wind up? I wind up at the point 0, -1. So this is the concept here. On the unit circle, your arc length is equal to the angle that your arc has cut, has been subtended by. Negative pi over 2 took me right there. Negative pi took me halfway around. An angle that was 3 pi. What do? Arc length of 3 pi puts me right there. So remember, on the unit circle, arc length, oops, sorry about that. Arc length equals your angle measured in radians. There's one last piece for us to cover. We're going to get to the stage where we're going to build a bunch of terminal points on the unit circle. And to start, I've taken these little pieces right here. These are 3 different hypotenuses, all of radius 1. This big thing is a unit circle. And you'll notice they're in red, blue, and green to match the red, blue, and green that you see here. These are all special triangles. So we're going to do a little bit of work to identify the dimensions of these special triangles, and then we're going to map them out and identify their terminal point on the unit circles. So I'm just going to build 3 of these right triangles. Let me go to green. It's a little bit thicker than I might want, but that's okay. Actually, my green is kind of giving up on me. Switch to a more effective green here very, very quickly. That looks a little better. So if you think about it, what I've put here is just, these are a little bit, my actual diagrams are a little bit bigger up here, but all I'm doing is I'm taking these triangles and I'm putting them right into the unit circle. Each of the hypotenuse that you would see in these 3 triangles is nothing more than a special right triangle with a hypotenuse of 1. This is going to be, and we'll do this in degrees for the moment, radians we do later. This will be 30 degrees, pi over 6 radians if I want. It's a 30, 60, 90 triangle. Up here, that's 60 degrees. In my green triangle, that's 60 degrees. Up here would be 30 degrees, but we're going to really just work about that, because you'll notice that these little inside angles, they all qualify as the respective bow tie angles when we put these triangles into quadrant 1. And by the way, over here, this is a 45 degree, 45, 45, 90 triangle. And if we remember our relationships, we should know the following. In a 30, 60, 90 triangle, the side opposite the 30 degrees is half the hypotenuse. This is 1/2. And what? The side opposite the 60, what do? You take the short side, multiply by the square root of 3. This length is the square root of 3 over 2, which would tell us if this is 0, 0, well, what do? We go over the square root of 3 over 2, and we go up 1/2. Over the square root of 3 over 2, up 1/2. And that tells us exactly what this red terminal point must be. In a 45, 45, 90 triangle, what do? Hypotenuse divided by square root of 2. 1 over the square root of 2, aka the square root of 2 over 2. That's true for both of the legs of this right triangle. So, in a 45, 45, 90 triangle, if I'm sitting at the origin, what do? I go to the right square root of 2 over 2. I go to the left square root of 2 over 2. Where do I wind up? At the point. Square root of 2 over 2, square root of 2 over 2. We got one more to do. Our green triangle. 30, 60, 90 again. What do we know about the 30 degree side? It's half the hypotenuse. There's where my 1/2 goes this time. And square root of 3 times 1/2 is what's going to be what? The length opposite the 60. So, on my green triangle, how do I get to my terminal point at the end of the hypotenuse that was built by this nice little cute angle? I go over 1/2. I go up the square root of 3 over 2. 1/2 square root of 3 over 2. And by the way, let's go ahead and mark these 2 poles. What over here? What do I know? My y-coordinate 0, my x-coordinate better be 1. This point is 1, 0. And what do I know up here? Gee whiz, my x-coordinate must be 0. My y-coordinate must be equal to 1. X squared plus y squared. 0 squared plus 1 squared equals 1. I'm in good shape. I've now started to identify a series of points on the unit circle. And if I did a blue bow tie diagram, I'd be able to replicate that square root of 2 over 2, square root of 2 over 2 to its symmetry partners in the other quadrants. I'll be able to build a red bow tie triangle in the other 3 quadrants. I can move the symmetry, square root of 3 over 2, 1/2. Its symmetry partners can be identified. And I can create a nice little green bow tie diagram and replicate via symmetry the point 1/2 the square root of 3 over 2. We're going to build that whole unit circle coming up, and we're going to find for all these different angles, we're going to be able to know their trigonometric ratios just by identifying the coordinates of these different terminal points.